Hello, it's Keith here, and this is lesson 79 of the platform-specific series of my Z80 assembly programming tutorials. We're looking at Mintile at the moment, which is my software minimal tilemap example. Now, today we're going to be looking at the Elan Enterprise version. Of course, much of the code for Mintile is multi-platform. However, there is a small platform-specific module, and today we'll be looking at the Elan Enterprise one, which is actually based on the Amstrad CPC one. The Elan Enterprise has a very similar screen to the Amstrad CPC. The screen resolution and the layout of the bits in what is the equivalent of mode 1 here is the same as on the Amstrad CPC. However, the screen memory layout is configurable on the Elan Enterprise. We have a line parameter table where we can map the memory out, and what we've actually got here is a much more convenient memory map, and so I think the Elan Enterprise version is actually slightly faster, which is nice. So we're going to be having a look at this today, and we're going to be trying it out. Okay, so basically what Mintile does is it allows us to have a tilemap which can scroll. If I use the right key, it will scroll, there we go. And it allows for X flipping of sprites. Now, Mintile does not support Y flip, it only has horizontal flipping, and that's because I was writing a game that only required horizontal flipping. It was a Chibi Fighter Street Fighter 2 parody, so it didn't need vertical flipping, and I didn't have time at that point to code it up. What I'm working on is a more enhanced version of this code, which is referred to as max tile, which allows for vertical flip. It allows for double height scaling of bitmaps. That's to save memory more than actually an effect, but it also does transparency, things like that. So it's a more advanced version. This is really the basic version, but this is perfectly adequate if you are creating a game that doesn't need vertical flipping, or if you're doing a game that really doesn't even require scrolling. It's a nice little simple example of how to get 8x8 bitmap blocks to the screen quickly on different systems. So that's what we're going to look at today. Okay, over to the code we go. Let's take a look. So the file we're looking at today is this Enterprise Mintile file here. Now, the first thing you see at the top is we've got various definitions for the multi-platform code, and we've got the screen base defined at C000, same as the Amstrad CPC. Now, what we've got is we've got a line parameter table, which is down here, and this is defining the screen size. We have defined a screen size of 256 by 192 pixels, the same as we did on the Amstrad CPC, and on every system where we can get that screen mode, that is what we use. Now, Mintile, as I've said in the other tutorials, basically works by drawing either the tilemap or the sprites as a series of strips. So we draw one horizontal strip per time. Now, the multi-platform code decides what strips need to be drawn and then sends the commands to draw those strips to the platform-specific code that we'll be looking at today. Now, when it comes to drawing a strip, if we are drawing an unflipped strip, it's the do strip routine that is executed. When we're drawing the entire tilemap, we just start at C000 for the top corner of the screen. But if we are drawing at any other location, we have a get screen pos function to do that for us. Now, the coordinates that are passed to the sprite drawing routine are an X and Y coordinate in what I refer to as logical units. One logical unit is 2 pixels. That allows us to have 256 by 192 coordinates with off-screen areas in a single byte for our 8-bit systems. So that's why we work in pairs of pixels. So what we're doing here is we're converting the logical units of the X coordinate here into a number of bytes. We work in whole bytes because that's going to be fast. We don't want to slow things down by making it working in half bytes here. So that's what we're doing there. And then what we're doing here is we are basically taking the Y coordinate and we are rounding it to a number of 4 lines. So the logical unit is in pairs of pixels, but we're working in sets of 4 pixels here. The reason we're doing that is the way the memory layout of the screen works. Every 4 lines we're going to have to update the H byte of the HL pair of the VRAM destination. Now this code is designed to be fast more than functional, so we are perfectly willing to sacrifice the granularity of Y movement. On a lot of systems we work in whole tiles, so this is really relatively trivial for an 8-bit system at least. So that's what we're doing there, and then we're simply multiplying things up and adding them to the screen base here. Now, the good thing about the Enterprise and the benefit over the CPC is we've basically got the screen memory laid out so that each line is 64 bytes below the previous one. That makes things very easy to calculate our screen position here. It also makes things very easy when we are drawing our strips to the screen. So this is the do strip routine, which will actually draw a strip of tiles. So this will be executed. It will draw an entire sequence to the screen, and then the calling code will execute it again to draw the remaining lines. So for the tile map, that will be run across the entire screen. For a small sprite, there is a miniature tile map. Everything is done with the same code, and that was it's not as fast in some cases as drawing sprites. It will depend on the complexity of the sprite, but what it is it means that there is just really a very small number of pieces of code that are platform specific, less support, easier to get your game working on more systems. So in this case we've got two, one for regular strips and one for flipped strips. If you didn't need the X flip, then you wouldn't even need that, and if you need Y flip and X and Y flip, you would need to write other versions of this code, which is what I've done for that max tile example that's going to be coming in the future. Okay. So the first thing we're doing here is we're backing up the stack pointer. We're using stack misuse. That's where we set the stack pointer to something else. In this case, we are going to read these pattern data for the tile that we want to show to the screen using the stack. Okay, now what we're doing here is we're loading the C register with 40 in hexadecimal here. Now why are we doing that? Well, this is 64 in decimal, and this is the amount that we need to add to the HL pair every time we move down a line. So that's going to save us some performance later on. Okay, now what we're doing here is we're reading the tile number from the tile map. Mintile uses a single byte for the tile number, and a tile number of 0, if it's for the tile map, is a tile that is unchanged. The tile map is actually a cache, and it represents the changes that need to be redrawn to the screen. So we don't want to redraw things that haven't changed, and they are written as a 0 when the cache is being processed. However, for sprites, we don't do that because the sprite tile map needs to be there so we can draw the sprite again in the future. Okay, so that's the tile numbers, and that's why we're checking if the tile number is 0 here and skipping if it is. If it's not, then what we've got here is the code to actually set the tile number to 0. However, there's a self-modifying code line here, and that will disable that line if we're drawing the sprites, because we don't want to 0 the sprites if we're drawing the sprite tile maps to the screen. Now what we're doing next is we're taking the H value and we're shifting it to the right until we've effectively multiplied it by 16. Now this is because there are 16 bytes per pattern. So what we're doing here is we're calculating the pattern data offset in memory that we need to use. Now the DE pair are the address of the base of the patterns. So that is the bank of patterns that we're using to draw our data to the screen. And so we're adding the HL pair here after we've basically effectively multiplied the value of the tile number by 16 here. That's what we're doing there. Now once we've done that, we are loading the address of the source pattern data that we've calculated into the stack pointer. So we better not be doing any pushing or popping from here on out. Okay, we're then flipping to the shadow registers here. Now the HL address in the shadow registers will be the VRAM destination. So what we're doing here is we're loading the L part of the HL VRAM destination into the accumulator, and that's going to save us some time later on. So basically what we need to do is we need to transfer 2 bytes from our pattern data for each line of the tile. The tile is 8 pixels wide, that's 2 screen bytes. So we're popping those 2 bytes here, and we're writing the E byte to the screen, moving across the screen by inking L, and then writing the D byte. We're then adding C to the accumulator. Now the accumulator is the L byte of the HL pair. And with C, remember, we loaded with the value 64, which is the width of the screen in bytes. So by adding C and then reloading L, we've basically quickly moved down one line. And we then basically do the same again. We're loading the E, D pair there, and from using the pop, and we're writing them to the screen. And we keep incrementing by adding C and loading that into L. And we can do that 4 times, moving down 4 lines. But then on that 5th line, we need to do a little bit more, because at that point the H part will actually need incrementing as well. So we add our C value here, which will basically cause the L part to wrap around. At this point we know that the H part needs to be updated, so we're inking H there, and that is basically fixed us up. So we're now on the 5th line down of our tile. We then do the same again for the next 4 bytes here. Now at the end, at this point, we're basically done. So what we're doing here basically is we are decrementing the H byte, the H of the HL pair. That is resetting H back to the position it was before we started drawing our tile. We're then adding 40 plus 2 here, and this is basically resetting the L part of the HL pair and also moving us across one tile, because we've drawn one tile. We now want to get into the position to draw the next one. And what we're doing finally here is we are decrementing IYL, which is the tile count for the line, for the strip, and we are repeating until we've drawn the strip to the screen. Once we've done that, we're restoring the stack pointer. Now we backed up the stack pointer using self-modifying code. You can see that all the way up here. We backed up the stack pointer using self-modifying code there, and so that is restoring the stack pointer. If we had a 0 tile, basically we're just skipping over that tile and moving across one tile on the screen, and then we are repeating. So that's how we're drawing our unflipped tiles to the screen. Well, what about the horizontally flipped tiles? Well, basically what we do is we process the tile map backwards, and we have a piece of code that will allow us to flip the patterns in memory quickly. Now, there were a couple of options for how we could do this. We could calculate in real time the bit shifts, but that would be very slow. So unless we were doing this very rarely or in times when it wasn't time sensitive, maybe drawing text to a title screen might not be a problem, but in game, X flipping like that's not going to work. We could also double all the tile data, but that's going to take a lot of memory. So the best solution, I think, for this case is we have a lookup table. Now this contains 256 bytes, and basically we are going to pre-calculate every possible combination of bytes and their flipped equivalent. So we are defining our lookup table here, and we're aligning it so the bottom byte of the 16-bit address starts at 0 and goes all the way to 255. Now what we then do basically is we take the L value of the HL pair as our source data, and we then calculate the X-flipped equivalent of that source data. And so we're loading A from L there, and we're then taking 2 of the bits that relate to a single pixel here, and we're shifting them into the X-flipped position. We're then taking another 2 bits of a second pixel here, flipping those into the opposite position, and we're repeating until we've flipped all 4 of the pixels within that byte, and then we're writing the result back to the HL pair. So what we've basically done is we've loaded into the address HL the X-flipped equivalent of the value of L, because it's byte aligned. Using that align command, our lookup table is now performing that operation. So when we want to do the flipped version of our tile drawing routine, here it is, do strip reverse. A whole strip needs to be flipped with this version. Max Tile will be able to do single tiles, but this version only does entire sprites. So basically what we're doing here is this time we're loading BC with the address of the lookup table. Now we actually only need to load B there, but for this case we're just loading BC. We're then calculating the source pattern data, which is exactly the same method as before, so nothing's changed there because we're going to flip the data in real time. We then pop 2 bytes of our unflipped data into D&D, and then because we've loaded BC with the address of the lookup table, if we then load C with the data we want to flip and read in a byte, we get the flipped equivalent because we use the L part of the HL pair as the source data to flip that we flipped. So we've now loaded in, when we load A from BC here, the flipped equivalent of the value that is in the C part of the BC address, and we then just write that to the screen. So that's written a flipped byte, and the only extra date code here to do that flipping is this part here. So that's pretty fast, and it only used 256 bytes, and we can flip absolutely any data we want now. So we then move across the screen by inking L. We then load C with the E part of the pair that we loaded. We then load the equivalent flip byte from BC, and we write that to the screen. Now, we can't do the same efficient version of our code as before for moving down a line. The accumulator is in use when we're doing this, and we can't use C because BC is in use as well. So we're doing a simpler moving routine here to move us down a line. Basically though, we then repeat as before until we've done 4 lines. We then increment H. We repeat in the exact same way until we've done all 8 lines, and then we fix up our HL address, and then we are ready to do the next one across the screen. Now we are moving this time from right to left. We're going backwards across the screen, but basically, as I say, this is all pretty much exactly the same, just using that lookup table to quickly calculate the X flip. Now of course a Y flip is actually a lot easier. We can just either start from the end of the pattern data and work backwards, or we can start from the end of the screen memory and work backwards as we wish. So it's actually the X flip that is harder, and as I say, my Max Tile tutorial, which is the one that's going to follow this, will cover X flip, Y flip and XY flip, so all combinations. But as I say, I think you could probably work it out if you need it from the example today. Go to my website, download the source code, the build script as always, and you won't use the source code in any way you can. If you can get parts of it and use them in your own code, go ahead and do so. You don't need to give me credit. Thanks for watching, and goodbye.